Hello and welcome to chapter 6. All right, I think we're moving along pretty well. Today's lecture will be on the network layer, layer 3 of the OSI model. So we're going to be talking about how packets traverse the network using routers, how does routers operate by looking at the destination IP address, consulting with a routing table, we'll go briefly over a quick review on what we did in chapter 2 on how to review on how to configure the router itself. All right, so our objectives will be routing, routers, and configuring a Cisco router, which we actually did in chapter 2, if you remember. So we'll be, let's see what happens here. So the network layer is, again, it's the layer 3 of the OSI model. And what it's supposed to be, that's the one that takes the segments from layer 4 and encapsulates them into packets. It places addressing, the IP addresses on those packets. It's responsible for encapsulating the segments and decapsulating those segments, pulling those segments out of the packet. And the big thing is routing, finding the best path to the destinations. That's why we usually consider routers our layer 3 devices, because they use or they inspect packets, the IP addresses on the package, to determine which is the best route to the destination. Okay, now there's only really two protocols that are out there, standards on how to encapsulate packets. There's IP version 4 and IP version 6. There used to be others, such as IPX and the old Apple Talk and the Connectionless network services. None of these are really used anymore. It's either IPv4 or now the latest IPv6. Okay, so IPv4 and IPv6, they set the standard on how to encapsulate the packet and where do you place the addresses so that routers that are running routing protocols know where to look for those attached IP addresses or the fields that are stamped on the packets to determine where these packets should go. Okay, so you got a segment that comes from layer 4, and when you add IP headers to it, it becomes a packet. Now, IP protocol, after it encapsulates the packet, what do? They just give those packets to the data link layer, and the data link layer encapsulates it, sends it out. They are connectionless, which means those packets will be sent without anybody, without the destination, without making any connection with the receiver. Best effort, meaning you send it up and you hope that the guy received it. There is no guarantee that the data is going to get there. Media independent also, they can travel, those packets can travel on any type of media, copper, wireless, fiber optic cable. So, again, let's say connectionless. IP packets, when they go out without letting the receiver that you are sending them data. It's like you trying to go to your friend's house without calling them. So he might be there, he may not be there, right? That's what connectionless is. And if he's not there, and your friend doesn't know that you're coming. So that's what connectionless communication does. But it's fast. You don't have to wait and make a phone call, wait for his receive and say okay for you. So it's connectionless. On the other hand, segments really take care of that. It's connection oriented. So if your packets may get lost too. Best effort delivery say, just send the packet as much as you can, and whatever you receive, that's okay. So some packets may be lost on the way. And that's a big issue with voice over IP. And actually, believe it or not, voice over IP will trying to make up what the packet is, the lost packets. And so is when you are streaming videos. They have good guesses on what the packets would be and make up the actual video accordingly. But we'll discuss that some other time maybe. So best delivery means you just send out the data and hopefully that the receiver receives all of them. Okay? And media independent means it does not matter. Those packets can travel on an Ethernet frame, on a fiber optic frame, in an 802.11 frame. It's the media independent, which is good. All right, coming back, you can take a segment and add an IP header. Then that means this is when we say those segments are encapsulated in packets. Okay, here is the fields that are stamped on an IPv4 packet. And as you can see, there's a lot of fields that are right here. For example, this indicates this is a version 4. This stuff is really mainly for voice over IP. Here's your IP addresses. The time to live is a number. This is an 8-bit number. See, from here to here is an 8-bit number. It starts at 255. Every time you go through a hop, the packet's decremented, which means you have 255 hops before you reach your destination. If your destination is farther than 255 hops, your packet is gone, lost. And because this is the best effort, if your packet got lost, no one is there to tell you that your packet never got to its destination. That's why later on they created another protocol called the ICMP, Internet Control Messaging Protocol. And that ICMP, when it sees that a packet TTL number reached 0 and it was thrown out, it creates a packet called echo reply, and it sends it back to the sender telling them, hey, your packet died on its way. That's when you get the statement timed out. Okay, so here's a whole bunch of different options, fields that are stamped on the packet itself. All right, here are a little bit more details that, these are good to know. You don't have to exactly know what they are for. You'll discuss, for example, these right here on the packet when you discuss voice over IP, but there's nothing in here to tell you if the packet is good or not to check the packet. You do that at the transport layer or at layer 2. That's why why bother doing it with the packet itself. You want to move data as quickly as possible. If you have downloaded Wireshark, this is an example of the protocol analyzer Wireshark. It's for free, and you can take a look at all the data. This is a typical packet that's being transported across the network. Now, IP version 4 is limited. It's as you probably already know, it's 32 bits. And 2 to the 32 gives you pretty close to 4 billion addresses. And we're not even close in using all 4 billion addresses. So there's not a lot of IPv4 addresses around. In fact, I think in North America, they have been exhausted. Now, ISPs, when they go to the regional internet registry, most likely they'll get IPv6 addresses from now on. They started doing that, I think, like a year or 2 years ago. Okay, so IPv4, the packet is unsecured, number 1. That means you have to add IP security to it. It's connectionless. There's not enough addresses. Because there are not enough addresses, we started using the network address translation protocol. So we could create private IP addresses that you cannot use the internet, and therefore you need NAT to translate you and give you a global address to get out. But IPv6, which was ratified in 1998, took care of all the issues that IPv4 had. And the number one issue, of course, is not having enough IP addresses. 4 billion is not enough. when you have 128 bits, 2 to the 128, look how many IP addresses there is. It's udecillion. I don't even know how to pronounce that. And it's actually a little bit more. They truncated this. So there's enough addresses to go on for a long, long time. All right, and remember, so no need for PAT when you have IPv6, no need for NAT. You have already IP security as part of the protocol, so your data is always encrypted when you are transmitting it. And of course, there's enough addresses available for everyone to use. And take a look here also. There are less labels are stamped on the packet so that routers don't have to I figure out, they got less labels to work with, so packets move much quicker that way. They simplified the header. All right, and here's your IP address. It's much, much bigger. Of course, it takes a lot more space than the IPv4 because the IPv4 is a 4-byte number, a 32-bit number. All right, here's the Wireshark sample again, IPv6. By the way, if you want to download Wireshark, it's wireshark.org. Just go and download it. It's free, and you can just put it into a network as a node. You can run it on your computer, and it will capture all the packets that are running in your network. And if they are not clear, if your data is not encrypted, you can actually see it. Wireshark will be able to capture all of that data. All right, so now we talked about the two different types of packets, IPv4 and IPv6. Those are the packets that get sent out by your NIC. Actually, your NIC encapsulates those packets into frames before they send them out. And who grabs them? The router. When the router grabs the frame and pulls that packet out, it inspects the IP addresses that are stamped on the packet, and they're trying to find the best path to the destination. So these two PCs want to communicate with the outside world. So what they do is they encapsulate their packet with the IP addresses stamped on it into a frame, and then they send the frame to the router. The router takes that frame, looks at the destination MAC address that's stamped on the frame, notices it's the default gateway, and then sends it to this port where the default gateway will get it. What does the router do when it receives the frame? It opens up the frame, pulls the packet out, and inspects the destination IP address that's stamped on the packet, and then the router will look up a chart called the routing table and try to match the destination IP address that was stamped on the packet with one of the entries in the routing table. And if there's a match, it will send it to that interface to go out. And then it goes from one router to another router to another router to another router. So the whole idea we're going to be spending next semester, we'll talk about that next semester. How does the router know that the packet should go, for example, west and not east and not north and not south? Imagine this. You are in a post office. Post office is like a router. You receive a package, which is a frame. You open up the frame. You're the worker in the post office. You open up that box, pull the packet out, and you look at the destination zip code that is stamped on the package that's inside that box, the frame. By the way, you take that frame and you throw it in the garbage. You don't need it anymore. Once you got the package that's inside that box, the frame, you pull it out, you look at the destination zip code. Then you have a chart that says if you want to go for, let's say you're in Florida, and you look at the IP address, and the IP address is 07011. That's a zip code in New Jersey. And you know that that zip code is located north. So you take the packet and you send it to a gate, an exit in that post office that points for the truck drivers that go north on 95. So they take that packet and they re-encapsulate it into another frame, and they send that packet, the box, the frame. Now it goes from, let's say, Orlando to Atlanta, Georgia, because it was north, because they noticed that the IP address or the zip code is north. So once it reaches the router in Atlanta, Atlanta will open up the packet, a frame, pull the packet out, inspect the IP address. They see that it's 07011, and then it goes north, maybe to, I don't know, the next hop, maybe somewhere in South Carolina. And from South Carolina, it takes another hop, it goes north. Did you ever track a package if you bought anything online, and because you're eager to get that package, you keep checking it, and you see that if you, let's say you live in New Jersey and that package is coming from Florida, it's taking the hops north. Why isn't it going west? That's because all of those different hops, they look at the zip code and they know that that zip code is north. Exactly how the networks work. Zip codes are equivalent to the IP addresses. Every location in the world will be given an IP address. Think of it that way. And routers act like post offices. That's what they do. They route packages from one network to another network according to the zip code. Routers, they route packets according to the IP addresses, and that's their job. This is your local post office. You have to have that. If you don't have a local post office, then they cannot, we call that the default gateway. You won't be able to communicate with the outside world. Okay? All right, so that's the default gateway, which means if you are not going to communicate with anyone inside your LAN, by default, you go to the gateway, to your post office, so you can send your data out. All right, you may have direct connection. You know, the data that you're sending to you maybe it's not, doesn't have to go to another router. Maybe it's on the east side. That's where your other LAN is. Let's go direct connection. Local network route or a default route means like let's say a local default route, which means if a packet, if let's say you got a package and you looked up the routing table and none of them matched, what do you do with it? There should be a default route. You send the data somewhere else, somewhere where they tell you if there's no match, just give me it, send it over here, maybe to the main office or something like that. Okay. So here is on the PC, you can find out, you know, the host routing table that you have by typing netstat-r. So this is telling you if you want to go, for example, to this network, it's on the link. All of them on the link. We usually never bother with netstat-r. We don't. I mean, that's a command that is really, in terms of routing, I think it's useless. But anyway. That's not for me to say. Here is a local link address for IPv6. Same thing. You type netstat-r, and you get all the networks and their destinations and where they're going to go. But typically, we take a look at the router itself. It's the router that decides where the packet should go. Now, this router has 3 networks connected to it. 1, 2, 3. And the best way to recognize, sometimes we call these LANs, subnets. So if you have a topology and they ask you how many networks are there, what you do is you count the interfaces on the router. So you have 1, 2, 3, right? 3 LANs. So each one of those should have their own network address. Now, this guy and this guy, the 225 and the 226 guys, they are both on the same network, okay? Links are always one network. So this guy also has 3 networks, 1 here, 1 there, and 1 here, right? So again, you count the interfaces on the router, and that will tell you how many networks you have. These 3 routers, these 3 networks are directly connected to this router. Okay, so really there's no routing necessary right here because you send a package and the package needs to go to this guy, it's directly connected. It's going to be very quick. It doesn't have to go to the next hop to reach the destination. So if you want to communicate with anyone that is directly connected, the router will take care of that. Okay. So, how do you display the routing table? By typing the command show IP route. Show IP route is the command that displays the routing table in a router. And you have to be at the privilege mode. So question number one that you have to answer. What is the command that displays the routing table? And the answer is show IP route. And it must be written at the privilege mode. Now, all of these are codes to explain to you what these routes are. For example, the letter D indicates that this router R1 has learned this entry in the routing table from a routing protocol called EIGRP. The letter C, if you look up the letter C, means it's directly connected. See, 192.168.10.0 is right here, 192.168.10.0. This network, which is directly connected to R1. But network 10.110/24, which is right here, that's remotely, that means R2 send that information to R1 using the protocol EIGRP, right? So this R1 saying, if you want to reach this network 10.110 with subnet mask /24, you need to send the data to this interface, 209.165.200.226, which means this next hop. Okay? We'll talk about these numbers in details next semester. This is called the administrative distance. This is really a metric that is calculated for bandwidth plus delay. This is how long ago, the time it took, how long ago I have learned, me as a router, have learned this route. And this is my exit interface, where it's going to leave from. The packet's going to leave from. So, when a packet comes in, I go line by line, checking to see the destination IP address that's stamped on the packet to see if it matches any of these entries. And if there's a match, you send it to the exit interface. Okay? So, here it explains to you, for example, here it identifies the network. How is it learned? C is for directly connected. D was for EIGRP. L is for local. This side tells you the destination network that you're trying to reach. And C tells you the exit interface, where the data is going to lead from. This is like in the post office. And if it says, when you grab that packet, and the packet says you're going to zip code 07011, and on his list it says if you receive the package going to 07011, send it to the north interface. So the north interface would be C, that's the north gate, that's where the trucks that take the package. This right here indicating the 07011. Well, actually it's not directly connected, obviously, if you're in Florida. And here it tells you how did I learn this, that the 07011 is north. I learned it by adjacent router telling me that. We communicated using the routing protocol EIGRP, for example. All right? Now, this one called is the administrative distance number. Again, the lower the number, the more trustworthy this path is. This number identified the metric that it used. In this case, it's bandwidth plus delay. This is the next hop address where who your neighbor you're going to be sending the data to, his name. This is like the Atlanta hop when you're sending the package to Atlanta, right? The time, like I said before, the amount of time elapsed since the network was discovered, how long ago I have learned it. And G is my exit interface serial 000. This is the gateway the gate that leaves to Atlanta. Okay? Next hop address means this is one hop, right? And this is the next hop address from R1. Okay? So that's the address 209.165.200.226. That would be the next hop address. All right, let's talk about routers now. Routers are the devices that Again, analogous to post offices. They are the one that route packets between LANs. A router is really like a computer. It has a central processor unit. It has an operating system. It uses memory to communicate with the CPU. So the whole 9 yards. Now, let's take a look at the difference between RAM, ROM, NVRAM, and flash. These are a couple of things. Let's discuss why do you need to know these. In the RAM, RAM is made up of the random access memory, made up of capacitors. I don't know if you guys know capacitors or not, but capacitors are little plates that can be separated by a very small area, and they can be charged up to 5 volts or even 10 volts. Now, the thing about the capacitors, as long as they have voltage applied to them, the charge will stay there. If you let go with the voltage, in other words, if you turn the power off, the charge dissipates, gone. So that means the data, if you want it to stay, you have to keep the power on. Okay? But the good thing about RAM, you can make a lot of capacitor in a very small area. That's why you can get, 1 gig, 2 gig, 4, even 8 gigabyte of memory right on a very small module. Now, the central processor unit always goes to RAM to grab data from the RAM to bring it in and to process it. So you want to have a lot of RAM if you want to run a lot of applications. And who brings in the data into the RAM and then gives it to the CPU? It's the operating system that does that. So what goes into the RAM? When you are running the operating system, when you load it, it goes into the RAM. When you're running the configuration file, we call it running configuration file, that goes into the RAM. Packet buffer, IP routing, ARP tables, anything that the router is interpreting right now, it's in the random access memory. That's what the CPU is interpreting and processing. Anywhere else, it doesn't bother the CPU. Okay? So if you type something into the router, it immediately goes into the RAM and it gets executed. It's never saved anywhere else. So if, let's say, you created a configuration file and you turned off your router, you lose everything. That's why we always have to save it and put it into the non-volatile RAM. The non-volatile RAM is really RAM, but with a rechargeable battery next to it, so that if you turn the power off, you don't lose the data. Okay? So that if you created a configuration file, you take it from the RAM and you place it in the NVRAM. And the configuration file that is saved in the NVRAM is called the startup configuration file. If you remember the command from chapter 2, how do you save your configuration file into the non-volatile RAM, from RAM to non-volatile RAM? It's copy running -config space startup -config. Now, read-only memory chips. Read-only memory chips are made up of transistors, hardwired transistors, and when you turn the power on, all these hardwired transistors, some of them come on, some of them turn off, so you got all your ones and zeros, and that's what makes up the program. Because they are hardwired, you can't really change the program that's in there, but it will always be there. And it's much faster to access data from a ROM chip because they're not capacitor and they don't have to be recharged all the time, refreshed, in other words. What's in the ROM chips? The post, the power on self-test, which we'll discuss in a few minutes. The core files of the iOS, in case you lose your operating system, your router will immediately goes to the ROM chip and execute some basic iOS files. This is like having a boot disk, or your computer is running in safe mode. It doesn't run the full operating system, just the basic to allow you to communicate with the device so you can fix it. And Bootstrap is also in there, by the way. Bootstrap is the one that goes out and try to find the operating system. Where is the operating system located? It's located on a flash memory chip. All right, so question number 2. Where would you find the running configuration file? The answer is in RAM. Where would you find the startup configuration file? In the NVRAM. Where would you find the full image of the Internet Working Operating System, iOS? In the flash. And where do you find Bootstrap and the limited iOS files and post, the power on self test? That's located on the ROM chip. All right, so there you are, and here's your power supply. Here is the wide interface, WAN interface cards. Could be the serial ports in here and here. The NVRAM is right there, the non-volatile RAM. This is your CPU, and so on. So it's pretty much like a PC, really. On the back of the router, again, we discussed this in chapter 2. I think we see some of this. This is where your serial ports to connect to the outside, the WIC cards, the WAN interface cards. These are the ports that allow you to get in and manage the router. We used the console port last week. These are the default gateways, the LANs, right? All right, so like we said before, you can connect to the router either through the Ethernets, the console port for management purposes, the auxiliary port if you have a modem, and the serial ports, if these are in there, right? The serial ports that you can communicate with the outside world. Okay, these, like I said, these are the LAN interfaces. Now the operating system does a lot of things for us. He does the addressing, interfacing, he does routing, we can do security with it, quality of service, resource management. So the router can do a lot for us. And you will see going into next semester, we'll do security, or you can set up a DHCP server on it. You can even do some DNS if you want to. You can set it up for VPNs as a firewall. So Cisco routers with the appropriate iOS running, it can do many things for you. All right, so the boot set. How do you when you cold boot the router? So in other words, when you first flick the router on, flip the switch on, what happens? These are the 4 things that happen. The first step that happens when you turn your router on is a program called the Power On Self-Test. The Power On Self-Test is a program that runs several diagnostic programs that are designed to test the hardware of the router to make sure everything is where they're supposed to be. Okay, and if you look on the front of the router, there is an LED, green LED that's flashing. If it keeps flashing, that means the post is running. Once it turns solid green, you know that the post is successful and everything is okay. It's not a thorough test, but it's a quick test to make sure that the hardware is where they're supposed to be. Then another program called boot. Now he's next. He kicks in and he starts looking for an operating system, and he will find that in the flash. If he goes to the flash and he doesn't find it in the flash, he hopes to find it in a TFTP server. Now, if it's not in a TFTP server, then you end up going into running the core files, the core iOS files. So if you ever turn your router on and you see the prompt that says ROMMON, ROMMON, you know that that Bootstrap did not find the operating system in the flash. Let's assume that Bootstrap does find it. When Bootstrap finds it, it tells the operating system load up, and that is step number 3. Is the loading of the iOS into RAM. Once the iOS into RAM, then the router will go and try to find a configuration file, and hopefully, usually it looks in the NVRAM. That's where the startup config is, and load that up. If it's not there and you don't have it saved on a TFTP server, Then you'll immediately go into the console, which means you have to create one on the spot. And you'll get a statement that says, do you want to continue with the auto configuration? If you say yes, then the router will start asking you questions, and you have to give it, you have to answer those questions according to what you need to configure. Typically, we answer no, and then we go on and start configuring our own. We will start creating our own configuration file. The show version output. The show version output is important because it gives you a lot of information about what the router has. Not only what version of the operating system that you got, here's the name of it. The name tells you, for example, the first part of the name tells you this operating system is designed to run for a 1900 router. The second part tells you what features this operating has, the latest features that it has, and then the third part tells you if it's been compressed or not, and if it's a bin file. Sometimes, let's say you are on a phone call with Cisco support, and the Cisco support want to know the name of your operating system. So you type show version, and you let them know. It tells you, for example, how much non-NVRAM has, and so on. And we'll take a look at, for example, the configuration register. If you want to, we'll talk about how to restore the operating system, or if you forgot a password, you'll have to work with the configuration register. So you can find out what the number is, and this number and the configuration number will be able to change. So this way we can bypass the configuration file that has a password that we don't know. We'll discuss that some other time. Okay? So there's a lot of information in here that you can glean from and get some information out. Okay, configuring a Cisco router, we've done that already in chapter 2. Let me just, so if you really, I'm not going to go through this now. If you want to see me do this, just go back and review chapter 2, because I do it with packet tracer step by step. So here, this is EN. When you type EN, you go to the config mode, you create a host name, you create a secret password to prevent users from coming into the enable password, the console password to limit users from trying to go in through the console port. They'll be prompted for the password, or the telnet password, the BTY password. So if somebody wants to get in remotely, they'll be prompted with a password, and the service password encryption is the one that encrypts the console and the BTY password. Message of the day banner can be created as well, and here's where you copy the running configuration to start up when you're all done. Remember, that has to be done at the privilege mode, right? That means copying the configuration file that you just created, that's in the RAM. You are saving it in the non-volatile RAM. That's where the startup config is. Okay, you type int gigabit 0/0. You give it the IP address, the description, right? The description is really not a command. It's just a remark or a comment, so that when you display the configuration file, you'll see what that command does. You type no shutdown. That means you want that interface to be active, open. If you leave it as shutdown, you'll see this in red. That means it's not open. Even if it's configured, no data will go through if it's administratively shut down. Okay? If you want to quickly take a look at all the interfaces on the router and how they are configured and if they are active, you type show IP interface brief. That is a good example, a good command to use. Okay? Manual up means the hardware is okay. Protocol up means the configuration is okay. For now, that's probably good enough for you to know. I mean, there's a little bit more details on that when you are troubleshooting a router. All right, remember, this is one LAN, because it's this one interface, and this interface is the default gateway for everyone that is attached to the switch. If you don't need to communicate with anyone, Therefore, you don't need your default gateway. Only when you need to communicate with somebody outside your LAN, you send your data to the frame to the default gateway, and the default gateway will send it to the other interface, and then, as you can see right here, it goes to the other LAN. Okay, so here constantly, and this switch needs a default gateway. If this person wants to remotely access or to manage switch 1, this switch needs to have this default gateway in to be able to come back and communicate. If you don't give a default gateway to switch 1, data will never be able to come back to this person, right? So you need that default gateway. And how do you do that? By typing IP default gateway and this address right here. You do that on the switch. Okay? And how can you remotely access? You type interface VLAN1, the IP address to the VLAN, and then you type exit, and then you type IP default gateway, this address right here. So, why do you need, question number, I don't know, was it 4? I think it's 4. What do you need to manage a switch? Well, you need to give it an IP address and a default gateway. How do you give it an IP address? You type INT, interface, VLAN1. It could be another VLAN if you created other VLANs. And then you give it the IP address. You type exit, make sure you're at the config mode, and you type IP default gateway. And then you'll be able to type telnet. This person will be able to type telnet 192.168.10.50, and he'll be prompted with the telnet password, with a DTY password. By the way, there should be a subnet mask in here, and this person should be in the same subnet as this guy 192.168.10. And that's it. All right, that's a pretty good chapter. Again, if you want to take a look at the actual configuration, I think we did a pretty good job on in chapter 2. All right, so please answer those questions and submit them. And I hope you are enjoying this. So we're getting close to doing subnetting pretty soon. So we'll be discussing that. And next chapter, I think, is chapter 4. That's also a short chapter. All right? All right. Keep up the good work. Don't forget to read your read the book, and if you have any questions, please write them down, and don't hesitate to ask. All right. And until then, I will see you in chapter 7. All right.